Guys, thank you so much. It has been such a day so far. Again, I'm Ryan. I'm one of the co-founders here with B-Sides with Matt and Paul and Chad. And thank you guys for seeing it through. We're at our closing keynote now. And I'm really happy to introduce this person because I kind of look like them and it's super cool. No, I'm really stoked, and just because when my brother would share some of this research, I was like, "Oh man, that is so cool!" Like, and I'm like, "Yeah, I get geeked out about it." So I really hope that you guys will be excited. So my brother is a PhD graduate from Michigan State University, and he was a cybersecurity researcher for Walmart Global Tech. He's worked on some national security, NSF grants and National Science Foundation, sorry. And he's recently got another award for IEEE with cybersecurity. Anyways, super cool stuff. I'm really excited just to be able to present and share what he's working on. So without much further ado, Dr. Chris Fennell. Of course, I am having technical difficulties. It's not coming up. Let me close this and bring it back up just a second. I did. I just did that. Yeah. No, I'm good right now. Let me try to get it up again here. I asked them about that, so don't get me started. Oh my gosh. Yeah, it's not coming up here. Of course, this is eating into my time here. Yeah, look at this or something. Just a second, I'm gonna have to. I am gonna reboot it. I am gonna reboot it now. That's literally what I'm doing right now. I had it up in ahead of time just to make sure that I was like, oh man, I want to make sure it goes and runs, and of course it does this now. Yeah, that's right. That's right. Oh, I wish I had a Mac for this. Oh, you're restarting? Yeah, we'll put it on there as a backup. So. Okay. You guys want to stand real quick, just for a second, like just to wake up at the end of the day? Yes, there's one person standing. Yeah, thank you. Yeah. So just stand, stretch, give a stretch break real quick. Don't go anywhere. You good? All right, here we go. All set. So thank you, Ryan, for introducing me. Guys, it is a pleasure being here today. Of course, my team's things pops up right here. Let me get started. That it's always tough presenting at the end of the day because people are like, we've listened to a lot. There's a lot of information, and of course, mine's the technical one. So like, I'm going to be throwing statistics and other things at you. And I was like, man, people are not going to want to listen to this. So I will try to be brief. If you have any questions, please hold it till the end. So I'll try to run through that. I want to thank BSidesFortWayne for inviting me and allowing me to present today. This is my first conference since the pandemic, and doing it in person. We did virtual, but this is really great to be able to be back in person, meeting people, talking to people, and it's just wonderful. So today I'll be talking about using open source algorithms for C2 beacon detection with Microsoft Sentinel. This was a result of the work I did with the Hunt team at Walmart, and is considered exploratory research. And see if I can get the slide thing to work. Okay. So a little bit about myself. I am a senior technical expert in cybersecurity at Walmart. I am on the Hunt team, which is now situated within the Security Operations Center at Walmart. I am a little bit different from my teammates on the Hunt team, as I am a security researcher. And I'm also consider myself an academic, and my work focuses on gathering empirical analysis. So mostly for publication, and hopefully that work affects policy. So I've been fortunate enough to have been published in some very good conference proceedings and journals, and my work is centered on usable security or how people use or interact with security technologies. So a brief overview of what I'll be talking about. I'll be going over the open source ML algorithms that are out there, a brief survey of the academic literature, then moving into choosing an ML algorithm for a specific case, and for what we needed was C2 beacon detection. And then in the second half, I'll be talking about the analysis I conducted through the results and using RStudio, and then finishing up with some concluding thoughts. So open source models. So what's the problem? From a technical perspective, the command and control beacons from tools like Cobalt Strike are really problematic in that they are useful for malicious actors to relay information, right? That's at the end of the day. They can do other things, of course, but it makes sense to want to detect these things from beaconing out. And so the challenge then becomes that they're difficult to detect, right? Because beacons can act like normal traffic. They can call and be named like normal processes. And so a lot of effort, and I say a lot of effort, you probably hear a detection talk at every security conference. So in some ways, this is following the stream of research. So at SANS DFIR conference in 2022, many of my teammates attended, and there was a session that spoke about using unique ways to potentially identify beacons. So I was like, oh, this is cool. There are different ways to think about beacon detection. And so the presentation used something called Fourier transformations, which is adapted from electrical engineering. And it could be used to detect beacons. And while the method was novel, it carried with it an implementation challenge. So first, someone needs to understand how Fourier transformations actually work. And second, simply downloading and processing vast volumes of data is a challenging endeavor. And so the scale of data at which enterprises operate are often much larger than typically presented at academic or even practitioner conferences. And so these complications only increase the difficulty of using a method like this. And so one possible solution to many security organizations is to implement and develop external data repositories that can be used for analysis. However, besides maintenance costs, the data repositories are disconnected from the live data, which sometimes requires data scientists to often complicate and transform processes to make the model useful. So one possible solution to this is using ML algorithms to be used in conjunction with existing security tools. So not having external repositories, but using within the tools that you already have. And so there are many commercially available solutions out there, from things like Splunk or Proofpoint, offers various different types of ML models or solutions. Pretty much if it's a security company in this space, they'll offer some type of ML solution, right? Quote unquote. And so the challenge of these tool sets is that they're often closed off, and it's unclear how these models actually work. And it can potentially impact usability. And so you have an example here of an open source one that exists on the web. And so what I do as an academic is like, all right, let's look at what people have already done. Let's look at the security literature. And so thankfully there are papers like this where Neela et al. And the other authors offer reviews of techniques being explored in the academic and practitioner communities. And so their work highlights that ML models often attempt to classify data into groups that are useful for analysis, like k-means clustering, principal component analysis. Those are just to name a few. And the goal remains the extraction
analysis, and processing of vectors established by a model. That is the purpose of some of these models in the ML space. And so by using machine learning models for beacon detection, security teams within an organization could potentially identify uncommon and unknown threats in a rapid and evolving landscape. So here we can see on the up here on the right is that there are in the paper there are multiple ML techniques that have been used, and so they really break down. And this is not really an ML primer, so I'll try to be quick on this. Is that there are multiple types of algorithms to consider: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is that each data point is labeled or associated with a category of value of interest. An example of a categorical label is assigning an image to either as a cat or a dog, right? We've seen some of these models before. An example of a value label is like the sale price associated with a used car, right? The goal of supervised learning is to study many labeled examples like these and then be able to make predictions about future data points. In unsupervised learning, the data points have no labels associated with them at all, and instead, the goal of the unsupervised learning algorithm is to organize the data in some way or to describe its structure. Unsupervised learning groups data into clusters, like k-means clustering, or different ways of looking at complex data so that it appears simpler. Finally, reinforcement learning is the algorithm that gets to choose an action in response to each data point. So as it gets a data point, a common approach in robotics, for example, is where a sensor reads something at one point in time is one data point, and then the algorithm must choose the robot's next action, right? So that's sort of a very rudimentary idea of reinforcement learning. And so on the right here, from the security literature, you can see that they use something called 0R, which is a benchmark tool, another classification algorithm. 1R, which is short for one rule. It's simple yet accurate classification algorithm that generates one rule for each predictor in the data, and then selects that rule within the smallest total error as its one rule, and then that rule then becomes the predictor for the next data point. Another one that you can see from the table there is naive Bayes, right, which is based in, comes out of the field of economics, or Bayes' theorem. Which then offers independent assumptions between the predictors. So you actually have to assume that there's relationships between each predicting variables. And so it's very helpful in understanding some models. And largely, the machine learning models are based off statistics. And so we think of it as complicated or nuanced tools, but they're really just algorithms that are largely based around means or sometimes regression models. And then finally, random forest and SVM stands for support vector machine algorithms, and they're supervised machine learning algorithms. So that's what the security literature as a whole offers. It says, okay, here are the things that are being used, and this was a nice meta-analysis that looked at what have we seen across the literature. So, another way to think about machine learning is, why do we even need machine learning at all? Why not use a discrete algorithm, a simple algorithm that simply takes an open source algorithm, but in case it uses a discrete to say, here's a normal algorithm that classifies things. Let's just classify it. Why does it have to be machine learning? And so traditional algorithms can be useful because it's enough to iterate through. And the question is, do you need a machine learning solution? And so oftentimes, you don't. You really don't. They're a specific tool for their specific job. So the goal here is that everyone hears, there's keywords, and if you've been in the industry long enough, you know that there's certain things that people like to consider. So, but if you consider the Microsoft approach above, which goes through the data from a very linear perspective, bring in your data, classify it, go through it, and let's get our data, filter it, sort through it, iterate through it. And for many tasks, that might be sufficient. So you decide to choose a model, and let's go ahead for the sake of it. We're going to explore using some of these models. So we choose an open source model. And in this case, we use the model that I showed up on the slide earlier. And this is a KQL query that was out there. It claims to be an unsupervised ML model. And we're like, okay, this is great. What do we do with it? Let's try and figure this out. And so for this exploratory research of beacon detection, we choose a model that claimed to be an ML algorithm. And so the primary goal of the ML model would be to attempt to cluster processes and domains into a source and destination pair, right? So we want what the process is calling out to and where it's calling out to, right? And so the approach is very simple. Look at the time and connection with the attempts between a source and destination and analyze if it's potentially malicious. Without machine learning, one could simply look at all of the network traffic and look at all and to see if any of it is reaching out to a malicious domain. The challenge for that remains that it's distinguishing malicious traffic is near impossible without the aids of certain identifiers. And so by classifying potential pairs, an ML model can identify and reduce the total number of pairs to examine over a given area, making it an ideal resource for a hunt team. And so conducting much of the computational burden with a central repository like Sentinel, or Microsoft Sentinel, is a benefit because the model can be built in real time. An example of this would be to conduct an analysis of the logs with a given machine or conducting analysis where the logs are aggregated. In this case, Microsoft alleviates the burden by using the KQL within a security tool, Azure, and like I said, it's Sentinel. As you can see from figure 1, this is the code from the model that looks for the timestamps in the network traffic and pulls such columns as the device name and process name. So we run the model and we get results. So the results come back, and now what do we do with them? We have a model. We said it claimed to run a beacon detection. Now what? We don't know what it is. We have no idea how to interpret or to control these findings. And so the results come back after several minutes because at a place like Walmart, it's very big and takes a lot of time to do things. And even though it's very, very fast, we're looking at a lot of different things. And so in this case, I was using it based as a hunt criteria for a certain domain, right, or a certain area within Walmart's many, 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 many domains. And so the query had to run several times in order to account for a time period of a hunt that we were doing. We were doing a focused hunt. And so this required multiple runs of the process. And then we ended up with an exportable list if we wanted to export it, so we can explore it further. So because I like to look at data and I like to mess with things, I'm going to use Python. And so the output from the KQL scripts outputs records, several records that could be potential beacons, right? So we end up with things that they identify as potential beacons. And so changing the variables of the KQL script allows for more or less transactions. However, running it with the multiple interactions, it turns out the default for this model and using the KQL seems like it got sufficient results. Again, we don't know how this is working because this is exploratory. And so from these columns here on the left-hand side, it can be clear that to make sense of the outputs will require further analysis. So the results include a delta list, which is the number of seconds between each beacon. And then through some exploratory analysis, I felt like the next logical step would be to create a regression model to determine how different the beacons are from each other. And so in order to do that, I need to translate the data from a short form to a long form, and each beacon call out that would get one record. And so this was made possible by using the pandas data frame within Python and creating a new data frame with the desired results. So there were two main outputs. One output that focused on the delta transformations, so the time between each beacon, and the other one were focusing on the domains themselves. And so these two outputs would be used for analysis in RStudio. And I chose RStudio, not Power BI, because that's what I was trained in. Now I'm actually switching over to Power BI. At the earlier talk, so when someone, our previous talk was talking about Power BI, I was like, oh man, I'm switching to that. Is that going to be bad? So anyway, sorry, that's neither here or there. So where to begin? So typically one way to start looking at data is that we just have to look at what the model calls a beacon. And so here we have here are the beacons in this case that are positively skewed, so leaning towards the left. And the total number of beacons that we pick out are a set of potential beacons. So we can just look at what the model kicked out to us as beacons. And many of the beacons have records for very quick delta times, so that's on the y-axis. And you can see that there's there are a fair number of beacons. There's over 200 here. They call out pretty frequently. And then you notice a few of the records there call out very infrequently, very, very slow, so up to several hours. And so where do we focus our attention? So by adding more data from the output, we can say, okay, well, let's look at the IPs, the destination IPs. And so we need to break down the data further. One way we can do this is looking at the IP record count of the data with the delta variance on the y-axis. So you can see here that the IPs on the right-hand side here, which unfortunately have been blacked out because I had to black it out, to give you an idea of the destination IPs, they're just the beacons that are calling out to these IPs. And so as you see here, that the seconds in which they call out can vary greatly, like the previous slide, except we get a little bit more granularity on what's happening here with each different process. And again, there's a lot of colors overlap, but it's just, we can see how the IPs are interacting. And so the green, the purple ones on there, you can kind of see, oh wait, those are very quick. That seems to be maybe interactive sessions, whereas the green ones at the bottom seem to be, they're less frequent, they're calling out way more, there's more time between each count. So again, going further, we can look at the data by looking at the device beacon it's calling out from. This is largely the same view, but the number of beacons that the model detect didn't overlap much. And so in this perspective, we have the device name. And we wanted to look, okay, well, what if the device name that they're calling from has multiple beacons calling out to multiple addresses, right? That's a fairly common technique. And so with the computers, we can see that they're calling out it to the same IT. So in this case, it didn't really change the results that much. But this just gets to graphing the problem. It doesn't really tell us how to interpret the beacons. And so one way to understand that is creating a linear model of the beacons themselves. And so the next thing we can do is look at things statistically. Here we create a linear model or regression model between the beacons to see what is different. And a regression model is very simple. It takes all of the data and it simply tries to draw a line through it. So you take a scatter plot of your data points and say, let's draw a line through it and see what we can get. And so here we have the time, which is our main, the time difference or the time delta, is the intercept where the model crosses over the y-axis. And so at each time, that is a variable that affects the model. So at each different thing that you see on the left-hand side there, we have, in this case, is device name, MacBook Pro, Jamf, MCPD, Tanium client. And what those statistics mean is that at the intercept point, there's 5,044 seconds. It seems to be the common time. Now, that's because there's outliers in there, and it's drawing that thing way up. And so it's just drawing a line through it. So this is where it is. But if you notice, when you go to device name and MacBook Pro, if the device name is MacBook Pro, their callouts are significantly lower, and the asterisks in there represent statistical significance. And so comparing to the other data points, if it's using Jamf or MCPD or Tanium or any of these other criteria that we've identified in the model, it doesn't really affect the model that much. And so what the R squared below means is that of the data, this model accounts for 0.4149, which is 4.1% of the variance. So this model can account that 4% of all the statistics in there is explained by this model. And that's not that much. That's really small. But when we're talking about lots and lots and lots and lots of data points, 4% is actually pretty significant. So it's a really interesting finding in terms of what we have. So in the case that we did infer that our devices of the activities on the MacBook Pro were significantly different than the beacon activity of the other device, inversely, the regression model also tells us the process types were not predictive of time. So Jamf, Tanium, Wave, the WDAV, oh, Damien, I can't even say that, Enterprise had very high p-values, which suggests that they're not really statistically significant. So using a Dash app for R, which is basically an interactive board, I was able to create an interactive graph. And this was really useful for our hunt team. And so what you can see here is that with the beacons, it tells you a bit about them. Looking at the images here, and I'm sorry I can't do an interactive session because that would mean I have to have access to the data. Hovering over the images reveals different information on the domains and even the device names. So our hunt team was able to look at each of these beacons and look at, okay, what's it calling out to and what are the difference? And so seeing it visually on the lower left-hand side, those are our interactive sessions. So we actually had to look at those. We needed to look at what were the potential beacons that are having these very quick interactive sessions. Turns out it was, a lot of false positives, but it gave us a different perspective on how to look at our data visually. And we're thinking, okay, this model says, here are the potential beacons, here are things that call out every once in a while. Maybe that's low and slow. We did catch a few things in there that we weren't expecting, which like things like updates and things like that were not supposed to be in there. And eventually this will be moved over into Power BI because I think our studio scripts can actually go natively into Power BI. So it'd actually be a really cool thing. So some concluding thoughts, right? As with any approach to use, this use of KQL is not without its limitations. First, the ML query based solely on MS Sentinel doesn't really use the learning aspect of machine learning, right? In the most basic sense, it's simply a classification algorithm. probably, at the best sense, it'd be an unsupervised model, right? That pairs the items based on the source and destination. We didn't really know that at the beginning. We saw a model out there that was available to us, and we said, let's explore it. Let's see what we can do with it. And that being said, even if we had different data sets from different areas, it isn't clear that a custom model needs to be created for one hunt versus another. So we compared the output of two hunts that we had, and the results were drastically different, right? And this is helpful in understanding that the limitation of these tools, that results are very much dependent on the context in which they were gathered. So second, the model doesn't really provide immediate insight for detection, but is better as a long-range reconnaissance tool. In other words, the reason that the delta time variance needs to take longer over longer periods to determine a call out by a potential beacon, you could certainly run the results of the model once a day, but you would be missing the beacons that call out for longer periods. So you want to run this thing for over a longer period of time. The purpose of this tool is to detect beacons that are attempting to call up by scanning for several days, even weeks. So is this a detection for a SOC? Maybe, but it requires some additional analysis to really look and say, what are we actually looking at? So finally, the way the statistics is used for this analysis is unproven, right? This is unknown. We've never, as far as I can tell, we haven't seen anything where they've looking at Sentinel beacons in this way. So we don't know if the statistics are being used correctly. It might be that statistical assumptions are being violated, and that results in a greater number of false positives. However, this could be countered by the fact that we do not know what we don't know. Statistical assumptions like normal distributions can be violated so long as it understood how it affects the results. An additional problem that we ran into was the skewness helps determine of any statistics. So I've shown a slide here that has the different ways in which data can be skewed. And so the median scoring, or MADM, is used in this model as a way to describe symmetrical or normal distribution. Using the median allows us to ignore that rule. However, the KQL query uses standard deviation in there instead of the MADM. And because that function doesn't really exist in KQL. And so what this means is that the calculations that are based on the average or the mean are based on the average or mean instead of the median. And that has central tendency violations. And so what this means in the short term is that the statistical ramifications means that the mean is sensitive to all the scores. So if you're using the mean, you're sensitive to all those outliers, which is probably why the model was so high. So that is a problem with using this type of method. So this work presents an exciting perspective in examining data from the macro perspective of our data at Walmart. However, it requires additional resources in order to understand what we're even looking at. Just taking the model and running with it gives you results, but it takes time and effort for a team to understand the results. You then have to work out the question, why? Why did the model give us this record? It's really not clear unless you open the open source code, which you didn't create. And so therefore we had to spending time with the model. So just getting an open source model is one step. You actually have to spend time understanding, what is this model even doing? This method may prove useful in examining other network traffic or other metrics that exist within Sentinel, which is actually one thing we're exploring right now. And so continual development of this model would be an advisement, and after 5 or 6 more focused hunts, we might be able to provide data that gives us a more common understanding of how to use these machine learning models within KQL, and then ultimately in larger data sets. So that is all I have for you today, and I'm open to any questions. I know that's heavy at that. Like, hey, anyone want to talk stats? Yeah, in the back.
So what's your next, can you talk about real briefly maybe what's your next project or how you're going to go
Sure.
from there?
I have backup slides for that. So one of the things that I'd like to do next is I have several projects with regards to this work. I'll continually be working with the hunt team as a way to provide sort of data insights and looking at different ways we can explore hunting, right? I love the hunt team. It allows me access to explore a lot of different things. So when we do a focused hunt in an area, I spend some time exploring what this area is, and I do not have the same background as my fellow hunt team members who are classically trained as incident responders. So I look at data differently. I look at data as like, okay, well, what is this data really saying? What are we doing with this data? How do we infer this data? And it really affects how we write the reports. So I'll probably do 5 or 6 more hunts with this data with this model by itself, just seeing what we can see. And we've already learned so much because internally we have our own reports, and it's been very, very useful. In terms of my other research, which I love to talk about, I'm doing phishing research on user behavior. So sort of similar to like a UEBA, but looking at phishing data I'm doing a survey. I'm classically trained in quantitative and qualitative research. So I'll be doing research on how phishing affects us at the organization. I have a previous project, which I'm trying to get published right now, looking at the skills and efficacies of a purple team or a red team and blue team. So that's stuff I'm trying to finish out from my internship 2 years ago with Walmart. And then I'm finally trying to publish my dissertation research. So yeah, great question. So, sorry, he read for, yeah, go ahead.
So did you find any beacons with this, or did you find beacons mixed with legit traffic, or what looks like legit traffic?
That's a great question. I wonder if I could actually talk about that. So the answer is no, we didn't find any beacons, but we found things that potentially could be. The problem with looking at historical data is when we go and look to see if things are actually there, they're not there anymore. So did we find something? We don't know. And there's so many different types of things we can look. So to give you an idea of what we did next, we had so Carrie Roberts, who spoke earlier on there. I had one of her helpers in the SOC actually spin up C2 beacons. Right? Does this model detect it? Does it let's try to do this? We'll run it a myriad of different ways. This is what bad looks like, right? So we need ground truth, right? I'm very big on ground truth. This is what bad looks like, and it does work. It does detect it. So kind of waiting for the area. The other challenge too, is we do focus hunts, right? So we're looking in particular areas. If I try to run this all across the entire data at Walmart, I'm not sure. It actually crashes because it doesn't. It's just too much. So it does work. It does detect bad. I think it's really, really good for smaller organizations where you can actually turn on all your logs and keep them on, and you're getting ingesting all this data. I think it would be really, really cool to use this model. So I think that's the upside. For an organization like Walmart, so I had to add so many different filters. We don't know if we're missing it, right? In order to operationalize, look at it. So we try to focus on smaller areas in order to get to that. So, sorry, you had a question? Yeah.
So I was wondering if there were beacons that were designed to call out randomly instead of at regular
Yep.
intervals. Do you think this would have caught that?
Yes, it does. We tested the jitter.
Okay.
So we tested the jitter for different things and various jitters up to 18 hours. And it picked it up, which was really cool. So I tried figuring out, I'm like, is there a way I can talk about that? And the reality is that it does work and it doesn't work, right? And so we won't know until it's a real threat actor. So we have an active red team, and I've been looking for them, but we don't know where they're operating or what it is. So yes, it does work out. In fact, we were able to pick up a beacon that only beaconed out every 2 weeks. And so that's really low and slow. And so if you think of the scale, Walmart has the largest surface attack area we're the largest private network in the world, right? And so we have so many places that could be potential surface, threat areas. And so to try to pick up those things that low and slow, that would be next level. Is this the way to do it? I'm not sure, but we are exploring ml.azure.com is a way to use KQL within the machine learning directly in the environment, and that's really cool. So I'm hoping next year or somewhere along the lines I'll be able to talk about that. Yeah.
Have you found early on, or even through this, find any potential biases that are also skewing your data, like
That's a good question.
Or assuming things to behave in a certain way, and so your models look for those behaviors?
Yeah. So initially we didn't know what we knew, right? Sure. There are some challenges. I don't know if I can talk to some of the things, but the way our architecture is set up, we could be potentially biasing it based off updates, right? Or different things. There's so much, how much traffic comes from updates? Like, it's just ridiculous. Or even the calls for updates, right? That's potentially, what I'd love to do is to really get an area where we turn on all the logging for Sentinel. and just say, these machines, let's just see what the traffic looks like here with these machines.
have to really discriminate down to a few things.
Yeah, and so, right, and so I'm the first person at Walmart doing this kind of analysis this way. So we just don't know. We're exploring it and seeing what's there. But we have thought a lot about biases and thinking about how does the data itself. And what's interesting to that question that I was just thinking about now is, since we operate in different countries, we operate internationally. It's different each time. So what's normal? We don't know. It'll have to actually happen after continual focused hunts.
I was wondering kind of how you're separating your known good from known bad, and then of course the anomalous stuff we're trying to figure out.
So we have several components within cybersecurity at Walmart, or InfoSec at Walmart, that we have various. So we have a DACI team. And so they do a lot of data loss prevention focus. So they have a different way of creating models as well. The way I'm creating the models is a little different. I'm using this open source method. The way I'd like to create models in the future might be using something entirely. But the known good and known bad is a sort of, if you know what you're excluding, what's somewhere in the middle, I think that would be the best. But no, not right now. We don't know what we know yet. So yeah. Yes.
Is this application where you can use like a GAN at some point, or are the two need like unknown?
I run it in like 2 minutes. So, and because I've designed everything to be automated, all I have to do is run the scripts. So it's really good. The one that we just pulled it off the web. You can search KQL beacon detection, and you'll find a number of different things to run. You can pull it down. What I was trying to do is understand, is this useful? Because, okay, you got lists that you want to go check. What happens if it gives you 3,000 beacons? You're going to go look at all 3,000? Is it even useful? And turns out it is useful. It is doing something really interesting there. I was just trying to understand it statistically, like, can we have a way where we can do it automated, run it through an additional analysis and say, here are the beacons you should really be focusing on. What was really helpful, I think, for the rest of the team was understanding, okay, what's high and low? What's really interactive sessions, and what's things that don't happen all that often? And we picked up some things that I can't talk about, but we picked up some things that we were like, oh wow, this is actually picking this up as a potential beacon. So that's worth exploring, but that's outside of the scope of what I'm talking about today. Yeah. Great questions, thank you. Oh yeah, it took you guys up. You guys should have told me. We're past 5. Thank you so much, guys. I really appreciate it. This was great. So.